Excellent. Okay, good morning. It's Monday morning from the 403 to the HAZ. Mr. Nelson had a restful weekend. Looks like we might be getting coronavirus under control. So timestamp it. Timestamp it to today is April something. I don't remember. In any case, I am filming this video for the third time now. Something happens, either my battery dies or my principal walks in. So that just means I'm gonna knock it out of the park. We are talking about logarithms. We've talked about basically how they work, how to deal with them, how to convert between the exponential version and the logarithmic version. So we know that y equals log c of x is the inverse of y is equal to c to the power of x. And this is what the inverse looks like, and we can interchange them. These are the same thing. So this is an important quality for us to remember when we're dealing with logs, because this is going to allow us to do a lot of solving, to solve a lot of problems. Here are my lovely logarithmic laws that I am going to draw upon as well when I need to do things. But the one benefit of logarithms is that they help us to solve exponential equations when we have a different base. So we recall that if I had something like 2 to the x is equal to 60, I could solve by x by just getting both of these down to the same base with different exponents. So 16 is the same as 2 to the power of 4. And I have the law that any base to the x, when it's equal to the same base to the y, that means that x is equal to y. Okay, so this is what I use here, and so when I do that, I can ignore the bases and I can just say x is equal to 4. That's great. But what happens when, for example, I have something like this? 2 to the x is equal to 9. Now, intuitively, I can tell, well, I'm never going to be able to get 9 down to an exponent with base 2. I'm just not. So this is where we start to use our logarithms to solve for these. So 2 to the x, I can take the log of both sides of this equal sign. And in doing so, I get log of, and it's just going to be a base 10. So log 2 to the x is equal to log of 9. And then I'm going to use this law here to get my exponent in the front. So x can now come down in front just using that law. Log 2 is equal to log 9. And then to solve for x, I'm just going to divide, because log 2 is a number. Log 2 is a number. It's like a constant. I can just divide it out of there, and I get x is equal to log 9 divided by log 2. And I can actually use logs on my calculator. The log button is right there on my TI-83, and I can just go through this, and I'm going to do it. Log 9 divided by log 2 is equal to 3.17. So 3.17, around that, okay? So that's how we are going to use logs to solve exponential equations when we cannot get them down to the same base. So let's do another one here. So what if I had 8 times 3 to the power of 2x is equal to 568. Okay? So the first thing here, I notice that it's 3 that has the exponent, not the 8 here. So I'm actually going to get rid of that 8 right away. Just something I know I can do. Because I can't multiply an 8 into something with an exponent. So many colors right now, okay? 568 divided by 8 is 71. So I have 3 to the power of 2x is equal to 71. Now, I'm never going to get 71 down to a base 3 with an exponent, because 3 squared is 9, 3 cubed is 27, 3 to the power of 4 is 81. 71 is never going to get hit. So what am I going to do? Take the log of both sides. And so when I do that, I get log of 3 to the power of 2x is equal to log of of 71. And then using my log here, I'm going to bring this 2x down in front, divided by log 3 is equal to log 71. And then I'm going to divide out the log 3 from both sides, which leaves me with 2x is equal to log 71 over log 3. And I could have divided the 2 out with the log 3, so I could have just divided out 2 log 3, but I just wanted to not confuse you. So then I'm going to divide both sides by 2, and I get x is equal to log 71, which is just a number. I can put that into my calculator, divided by 2 times log 3. And when I type that into my calculator, log 71 divided by 2 log of 3, whoops, log 71 divided by 2 log 3 is 1.94. You have to be careful with brackets when you're putting this into your calculator. So just make sure you use enough brackets to isolate what's going on. So 1.94, approximately. Okay? So let's increase complexity. What's going to happen now when we have exponents on both sides of the equal sign? Let's see how that plays out. So we'll just do one more, just to drive it home. What if I had 2 to the power of x over 3 is equal to 11? Again, 11 is a number I'm never going to get down to a base 2 with an exponent. So I'm going to take the log of both sides. Log 2 to the power of x over 3 is equal to log of 11. And then I'm going to use my rule here. X divided by 3, log 2, is equal to log 11. Now I'm trying to isolate for x. So I can either get rid of the 3 down here by multiplying both sides by 3, or I can divide by the log 2 first. It doesn't matter what order I'm going to do it in. This time around, I'm going to multiply both sides by 3 first. Okay, so that's going to cancel. And now I have x log 2 is equal to 2 log, is equal to 3 times log 11. Now I can divide out the log 2. And I get x is equal to 3 log 11 divided by log 2. 3 log 11 divided by log of 2 is 10.3, is approximately equal to 10.38. And I can check my work by just basically putting 10.38 in for x and making sure that it's going to give me 11. So 2 to the power of 10.38 divided by 3 is equal to 11. That's all I have to do. So this is my answer right here, which I'd like to put a nice box around. Okay, now let's increase complexity. Not by a lot, quite straightforward still. Okay, so what happens when we have exponents on both sides of the equal sign? So what if I had, I like black. 4 to the 2x minus 1 is equal to 3 to the x plus 2. Okay, eye contact. Here we go. Different base. These are as small as, well, I could get this down to a 2, but who needs to do that? I don't need to. What I'm going to do right off the bat is just take the log of both sides. Okay? I've taken the log of both sides. Now, I'm going to use this law to get the exponents down in front. Because 2x minus 1 times log 4 is equal to x plus 2 times log 3. Now what I have on either side is a binomial multiplied by some number, like some constant number. So just like if I had 2 times 2x minus 1, I would multiply 2 by 2x and negative 1 by 2. So I'd get 4x minus 2 if I did this multiplication. Well, this log 4 and this log 3 are just like constant numbers. They are numbers, constant. So I can just go ahead, because right now this is pretty useless to me. If I divided out the logs from either side, I'd still wind up with a rational expression. I'd have 2x minus 1 over x plus 2 is equal to log 3 over log 4, if I was to start dividing stuff around. That's not going to help me. What's going to help me is expanding out the multiplication here, and kind of isolating the terms. So when I do that, I get, is this a good red? I get 2x times log 4 minus 1 log 4, or just minus log 4, is equal to x times log 3 plus 2 times log 3. Now what I'm going to do is move all my x terms over to one side and all my constant numbers over to the other. So this negative log 4, I'm going to add log 4 to bring it over here, and I'm going to subtract x log 3 to bring it over here. So when I do that, I get 2x log 4 minus x log 3 is equal to 2 log 3 plus log 4. Now, what I can do here is I'm going to factor out my x. I have an x in common. It's the only really thing I have in common here. So I'm going to use my common factoring to get that out of it. So I'm going to pull out an x. X times 2 log 4 will give me 2x log 4. And then x times a negative log 3 will give me negative x log 3. And that's all going to be equal to this here. And to isolate for x, I can just divide out this whole term here. 2 log 4, because it's just a number, minus log 3. And I'm going to divide that over here, 2 log 4 minus log 3. That becomes 1. And this is what x becomes equal to. So then I can get rid of all this, and I get x is equal to this. Which, if I throw it into my calculator, I get 2 log 3 plus log 4 equals, divided by, open bracket, 2 log 4 minus log 3, double close bracket, is 2.14. And again, if I replaced x with 2.14 here, I would get these two sides equal to each other. Okay, let's do another one just like that. Yeah, let's do another one. Okay, last one here. My coffee hasn't been in the way. Delicious coffee. Okay. So let's say I have 4 times 7 to the x plus 2 is equal to 9 to the 2x minus 3. This is going to get really ugly, but we're going to do it anyways. What's going to make it ugly is this 4. But it's not going to be so bad. So, first step here I want to do is I don't want, where should we start with this one? going to start by dividing it out. I actually don't know how this one's going to play out, but we're going to try it. So I'm going to divide both sides by 4. Okay, and then that's going to disappear. So I am struggling here. I get 7 to the x plus 2 is equal to 9 2x minus 3 over 4. Okay, and well, okay, you know what? I'm going to back this one up, okay? Because we're going to have to employ one of these laws here, and I prefer to use this law over this law. Just a personal preference. So what we're going to do here is dividing out the 4 is not going to do anything for me because this is an exponent, so I can't divide an exponent by 4. So I'm going to take the log of both sides. Okay, 4 times 7 to the x plus 2 is equal to log of 9 2x minus 3. Now I could have done the division and used this law on the other side, but I'm just going to use this law up here. Okay, so I have log of a times b. Log of a times b. So I can rewrite that as log 4 plus log 7 to the x plus 2. Okay, and that's equal to log of 9 2x minus 3. The next thing I can do is bring down the exponents using this. So this log 4 is just going to stay out there, and we're going to move over. Log 4 plus x plus 2 log 7 is equal to 2x minus 3 log 9. And now, just like in the last problem, I'm going to expand these out to separate the terms. So I'm going to do my binomial multiplication. This log 4 is just going to stay there for now. So I'm going to multiply x times log 7 and 2 times log 7, 2x times log 9, and negative 3 times log 9. And when I do that, I get log 4 plus x log 7 plus 2 log 7 is equal to 2x log 9 minus 3 log 9. And now what I'm going to do is I want to collect all my x's on one side and all my constants, or just my numbers, on the other. So I'm going to move this 3 log 9 to this side, and I'm going to subtract x log 7 from this side to bring it over here. And when I do that, I get log 4 plus 2 log 7 plus 3 log 9 is equal to 2x log 9 minus x log 7. And now I'm going to just factor out my x here. So I get log 4 plus 2 log 7 plus 3 log 9 is equal to x. X times 2 log 9 gives me 2x log 9. X times negative log 7 gives me negative x log 7. Now, all I have to do to isolate for my x is divide both sides by this. Okay, and this goes away, and here's my answer. And that answer, if I put it into my calculator, gives me approximately, so log 4 plus 2 log 7 plus 3 log 9 divided by 2 log 9 minus log 7 is 4.85. So that means that if I substitute 4.85 for x, when I solve this side, it should give me that. So what is 7 to the power of 4.85 plus 2 times 4? That gives me a really big number. So this, when I put that in, it gave me 2,460,263. So I should get a similar number there when I do this, so I get 9 to the power of 2 times 4.85 minus 3. And I get 474,143. And they're very close, and this difference that I'm getting here is only because I didn't keep more decimal points. So if I would have kept more decimal points, this number would have been much more accurate. But that is telling me that, yeah, I'm pretty darn close there. So I am happy with this 4.8 approximate answer. And this is basically as complex as it gets for this unit, for solving exponential equations using logarithms. So the next video, we are going to start looking at solving logarithmic equations. And we'll have to end up using what we know about exponents and about the inverse relationship. So until then.